my name is Easy-Cali, and here is a presentation video for our work, EasyGaze3D, towards effective and flexible 3D gaze estimation from a single RGB camera. Our goal is to estimate the 3D gaze direction in the camera coordinate system from the input image. The existing gaze estimation methods mainly include three categories. The 2D regression-based method aims to regress the point of gaze on screen. These methods are usually susceptible to head movements and missing 3D spatial information. The 3D model-based method estimates the gaze direction based on a geometric model, which can achieve a reasonable accuracy, but they usually require dedicated hardware, hence limiting the application scenarios. The appearance-based methods only use an RGB camera, and usually apply deep models to derive the gaze, so that they require large databases to train the model, and can be greatly limited on the unseen data. Here is the overview of our method. We detect the 2D facial landmarks from the input image and recover the 3D facial shape of the human target. Then we can calculate the extrinsic camera parameters, which enables the transformation between the facial and the camera coordinate system, also named FCS and CCS. Without loss of generality, the eyeball can be considered as a standard sphere, so the spherical fitting is applied to the vertices within the eye contours to obtain the eyeball centers. In the following, we transform the FCS coordinates of the pupil and eyeball centers to the CCS, as well as the recovered 3D facial shape. Then the unit vector pointing from the eyeball center to the pupil center can be computed, and the 3D gaze direction is output as the average vector of two eyes to minimize the estimation error. To further enhance the performance, we propose Easy-Cali, a flexible calibration module. It aims to derive the subject-specific features in advance and enhance the stability and effectiveness of the framework. In the calibration process, the subject is instructed to keep a constant fixation at the center of the camera lens, and will be taking a series of images by this camera. Unlike many common calibration methods, the subject is not required to keep the head fixed or look at many calibration points, so that the whole process is very easy to perform. According to the simplified eyeball geometry and the pinhole camera model, when the subject fixates at the camera lens center, his or her eyeball center, pupil center, and the camera lens center will lie on the same gaze line. Hence, the projection of this line on the image will coincide with the 2D pupil center, no matter how the subject moves the head. According to this, for each calibration image, we can detect the 2D pupil center. Then the gaze line can be derived. We solve the camera extrinsic parameters using the recovered facial shape and landmarks, and the gaze lines on each calibration image are transformed into the FCS. Since all the gaze lines are supposed to pass through the eyeball center that is fixed with the facial shape, we compute the intersection point of different gaze lines as a calibrated eyeball center. Finally, the features are input into EasyGaze3D instead of the original 3D facial recovery and spherical fitting steps, which can reduce the running time for each frame and enhance the performance. Here are the experimental results on the IMR-Cali gaze dataset built by ourselves and the public dataset MPI face gaze. We compare the average angular error of our method and several existing deep models. The results evaluated on the first dataset show that our proposed EasyGaze3D with Easy-Cali module achieves the best performance among all the methods. And the results on the public dataset indicate that the basic version of EasyGaze3D is also comparable with the existing methods. It should be noted that our proposed system can be plug-and-play and has no requirement on training with large-scale dataset, which is a prominent advantage over the deep-based models. These are the gaze estimation effects of EasyGaze3D. Our method can achieve good estimation performance and robustness on different gaze directions, head poses, image qualities, and illumination conditions. These are the real-time gaze estimation effects. The EasyGaze3D with the Easy-Cali module can achieve a running speed of 96 fps on 720p input size, showing high efficiency and real-time performance of the proposed method. That's all, and thanks for watching the video.